First question. A force of 800 newtons stretches a certain spring a distance of 0.2 meters. What's the potential energy of the spring when it's stretched that much? Okay, what's the equation? Again, this is the easy way. What's the equation or the easy stuff? Come on. What's the equation for the energy stored in a spring? Yeah. E equals 1/2 K. K. Am I given K explicitly in the problem? Not yet, but am I given enough information to get it? Yes, I am given the force, and I'm given the amount of extension it went through by that force. So on the side, I'm just going to go K equals 800 newtons divided by 0.2. What's that? Well, that's kind of like dividing by 2 and then multiplying by 10. Because okay, dividing by 0.2 is like dividing by 2, and then, but it's 10 times bigger because you're dividing by 0.2. So that's how much? What's 800 divided by 2? 400 multiplied by 10? 4,000 newtons per meter for this spring. And now we just plug in the numbers. Half 4,000 times 0.2 squared. Okay, how much is that? Well, 0.2 squared is 0.4. Yep, 0.4. Sorry, 0.04, my bad. 0.04, 0.02. Yep, so how much? 800. Yes. $800 joules of energy. Is it 800 or 80? Not 40%, 4%. Yeah, 0.04 is 4%. Yeah, 04, yeah, that's the thing. Yeah, yeah. 0.2 squared times, yep, it's 80. Yep, 80. Yep, 80 joules. Great. What's the second part of the question? What is the potential energy when it's compressed 5 centimeters? Well, same thing. And we don't have to calculate the K because we already have it. So EE equals, again, 1/2, and my K is 4,000. But now my compression is 5 centimeters, or 0.05 squared, which is 0.05 squared times 0.5 times the 4,000. Just 5 joules. Okay. Sorry, say again. Okay, everyone, listen up. Perfect. Amar is saying the first one had a what? Had a stretching situation. This one is what? So in university, yes, you cannot call both of them what? Positive. One of them has to be what? One of them has to be, depending which one you want to take what the positive direction as. Is the positive direction when you push it in, or when you what? Pull it away from the natural position. So, but so mathematically speaking, no one would know. Physically speaking, with a long answer, show your work, they might actually what nail you on that So that doesn't make sense. It has to be what, positive directionality or negative. Well, you know what? If it's a multiple choice, they have no idea what you did anyway. But you're absolutely right. Technically, one of those should be negative. Either one, depending on your designation of positive. Nope, never does. Did it matter when we did kinematics or forces? No, there is usually what, a good choice, sorry, a better choice, but never an impact on your final answer, especially when you get squared. Okay, we have 2 problems left. This one and this one. Everyone, I'm gonna do this one for today. Okay, this definitely looks more interesting. Okay, so boom. Okay, so what's happening here? The question is saying a 2-kilogram block is pushed against a spring. So the first thing you do is what? You push it against a spring and you hold it. You are holding. The force, again, that's a third name. spring constant, stiffness constant, or what? Force constant. All of them mean the same thing. It's a K, and it's 400 newtons per meter. Okay, compressing it, sorry, by 0.22 meters. Then you what? You what? You release your hand, which means what's going to happen to the energy inside of the spring? It's going to what? It's going to be released. Okay, it has to be. It's potential, which means it's stored. It gives away. All right. It moves along a frictionless horizontal surface, and then up a frictionless incline. We could have added friction to this, no problem. With a slope of 37 degrees, right there. What is the speed of the block as it slides along the horizontal surface before touching the ramp? Okay, and then how far does the block travel up the incline? Okay, everyone, a caution about wording. Travel up the incline. So are they talking about this distance or this distance? Exactly. So you actually have to kind of like find, it's a hypotenuse issue, not a height issue. Okay. All right. How would we, again, what's the main principle of energy conservation problem? What do you do? What was the magic word you used? How do you look at any energy conservation problem? You trace. Okay. So everyone, let's look at this. Everyone, eyes on me. You compress. You're holding, and then you release. At the moment you release, was the block moving? No, because technically it's immediately limits immediately as you are holding it. Okay, so EK right there is what? 0. Was it compressed? So EE is somewhat some positive number. So EG, it's exactly on the what? On the ground. Okay. Pushes, pushes, pushes. And then what? At some point, what happens to the block? By the way, the block is not attached to the what? By the way, what happens if the block is attached to the spring? Would it ever leave the spring? No. What would have? It would extend and go what? Back and forth, simulating what kind of motion? What do you call a motion that repeats itself? Cyclic, but what was the periodic motion? Okay, by the way, that has a name called simple harmonic motion. Simple, get used to this word. SHM. We're going to do it next week. SHM, simple harmonic motion, which is motion that happens at one single frequency. At one single frequency. Not like your heart EKG, which is a weird wave. By the way, any wave that doesn't look like a perfect sine or what? Cosine wave is called a complex harmonic motion. Any wave that looks like a what? A perfect what? Perfect sine or a cosine wave is called a what? Simple harmonic motion, because it happens at one single frequency and that's it. Yes. Okay, so if there was absolutely no ramp, it would go on forever. You're absolutely right. The question is saying, at what speed does it leave? Does it what? Leave the spring. Okay, so now let's think about this, okay? Obviously, if it's got to leave the spring, it's got to leave the spring when? So imagine if it's basically what? The spring, as it reaches its what? Its natural length. Let's say the natural length initially was here, and then it leaves, okay? Now, when it leaves, does it have motion? Yeah, probably not just motion, maximum motion ever. Does the spring have any stretch or compress in it? No, because it came back to its what? Natural length. How about EG? Still what? Still 0. It keeps, now it starts what? Going up the ramp. As it goes up the ramp, what happens to the EG? What happens to the EK? So at some point, it's going to have to come to a what? Exactly, because EG will max out at some point, which means your elevation will max out at some point. So everyone, let's, so for part A, okay, E T initial equals E T final. But my final now is not at the top of the ramp. My final now is where? At the ground, at the moment it leaves the spring. So technically, you can still show me EG, but you can always just call it 0. So EKI plus EGI plus EEI equals EKI plus sorry, not I, F. F plus EEF. Which two of these are 0 all the time? All the time. Sorry, not all the time, as long as you're on the ground. Gravity, thank you. So everyone, I'm going to cross this one out and this one out. Oh, absolutely, completely up to you. I'm just taking it easy today. Yeah, and you're gonna see so many notations. Take whatever you like. Okay. Oh, initially, what was the EKI? What was the initial EKI before release? 0. Thank you. Yep, all the energy was elastic. Okay, at the moment it leaves, the spring goes back to its what? Natural equilibrium length, which means what? No stretching, no compressing, which means what? E would be what? Come on, when when the spring has no compression or stretching in it. 0. Yeah, oh yeah, the ramp so far doesn't exist to us. We're only talking about the horizontal surface. Yes. Okay, let's play with the equation. 1/2 k delta x squared equals 1/2 m v squared. By the way, everyone look, you can call this I if you want. You can call this F if you want. You don't have to because these are the only X's and V's we have. What can I cancel from both sides? Yeah, by the virtue of what? Multiplying the whole equation by 2 on both sides. Either way you think about it, feel free to go like this. Cancel, cancel. All right. What are we solving for here? We have 4 variables, everyone. Speed, yes. So can someone tell me how to arrange for speed symbolically? Come on. Symbolic. Ammar. V equals root. So K delta X squared over. Yep. So everyone, one shot. Vf equals S square root of, you said K delta X squared I over M. Done. Let's plug in the numbers. I'm going to do it in one shot. Actually, you know what? Which means I can just find the answer. And the answer obviously is going to be a speed, so it's meters per second. All right. K is how much? 400? Okay, what was the compression? What was the delta X? So I'm going to do that first. 0.22 squared times 400 divided by how much mass? 2 exact. All right. And we take the square root, which is going to be 3 point something, as you can tell. What's the specific situation of all the numbers we used here? What? Oh, 400. Okay, now that's bad, right? So let's say we keep it at least up to 2. So what will it be? 3 point. All right, good. Oh, you would never see that on my test. I know. I would never give you what less than what 2 sig figs for absolutely any value. But technically, yes, if that is what the question is, and you're taught the same sig fig rules in university as here, you have to make it 2. Sorry, you have to make it 1, which would only be what? Would be 3 meters per second. Yes. Okay. Part B. Can someone tell me what's part B asking for? Huh. How far? How far? Where? Where? Up the ramp. I can't do that first. I have to find what first? The what? Not how far it travels up the ramp until it stops. More like what? At what height does it stop? Do you see what I mean? And then I'm gonna do a quick SOHCAHTOA. All right. So what are my? Everyone, we can go here now. Okay. Everyone, for part B, you still want to say ETI. But now, where is your final instant when it goes what? Up the ramp. Now, when it stops, what's the EK? Also, is the spring under any problem now? So both EK and EE are 0. The maxed out one is what? EG. Now, which ETI could you take? Could you take your ETI to be the very first one? What do you think? Could you take your ETI to be the moment it leaves the what? It leaves the spring? Yes, you can, because ET at any moment is conserved. Let's go back to the very what? Yeah, so all of the elastic energy at the very beginning is equal to the EG at the very end. All right. So no, I want to never cut off a question. I want to hear the whole thing. Exact. But what you're right. What if I added friction there? Now you're what? Now you're forced to use the what? The ET as it left the what? As it left the spring. Because some of it was burnt or wasted when it traveled as it was pushed. 100%. You good. All right. So let's go back all the way to the beginning. So obviously, okay, I'm not going to bother you now with EK, EG, EI, and crossing out. We know which one's going to survive. Which one survived from the very beginning? E elastic. So go ahead. E elastic must equal EG final. Okay, well, that makes it very easy. 1 half K delta X squared I equals mg HF. Sorry, HF. What are we solving for here? Height final or Lagrange final. Can you tell me what's the arrangement of the equation then? Come on. Uh-huh. Yep. All of that. H final equals 1 half K delta X squared I over mg. All right, let's do this in one shot. Obviously, I'm going to start with 0.22 squared. Let me clean up. 0.22 squared to the power of 2 times K, which is 400, times half. Same initial energy as before, of course. Now we divide it by, this is where people make mistakes. If you want to do this in one shot, what should you use now? You should use brackets because you can't just divide. Because if you do divide it by m times g, it's going to divide by m, but it's going to what? Well, because it sees the string and it finishes step by step. No, or you can what? You can divide and then divide again. You know what? Let's just use the bracket. Bracket. The mass was, you said 2 times the 9.8, which is basically the weight. Boom. 0.493. So let's go with 0.49 meters. But that's how high it stops. I want to know how far it stops. What should I do? Come on. It's a right triangle. All ramps are right triangles. Hmm? For the the 0.22. The very, very, very beginning. So let's sketch a quick right triangle. Oh, my bad. Right triangle. Thank you. What's the angle? 37. Is it 37? 37.0. Oh, okay, so 37.0. We traveled up 0.49, and I'm trying to find this one. So or ka or toa. Well, depending. Let's label. What am I trying to find? Hypotenuse. So we're trying to find the hype. And we do have the opposite. And the adjacent is completely irrelevant. So I need to relate those two. Which one? Oh. So OH. So katoa. So what do? You just do sine of 37 equals what? O over, so 0.49 divided by hype, or sure, yeah, hype, fine. Hype. How do you solve this? Not much. You crisscross. You're going to end up having to divide the 0.49 by the sine of 37. So the hype is equal to, I'm going to do it here. We're going to divide 0.49 divided by, I have to put a bracket, and I have to do 37 trig sine. Do I need the shift? No, why not? Because am I using an angle or finding it? If you use it, you never use shift. If you're trying to find it, you use shift. Boom. It climbs up 0.81 meters up, on the ramp. 0.81 meters. That is the distance. Welcome to energy conservation with springs. On frictionless surface, I should always add. When we do the unit review before the midterm, sorry, for the test, I will show you how friction obviously messes up, but also adds more work, literally and figuratively, more physical work and more work in the math.